Large language models, they're amazing. They can be poets, translators, brilliant conversationalists, but there's this one thing they are just consistently terrible at: planning. Turns out, even the most advanced AIs can totally fail at simple logic puzzles. So a group of researchers had a thought. What if we stop trying to make the poet do math and just, give it a calculator? So how in the world do you give an AI a calculator for logic? Let's break it down.
So to really put this to the test, researchers took a classic AI challenge, the blocks world problem. The goal is super simple. Just rearrange the blocks you see on the left to match the pattern on the right. Seems easy, right? I mean, you'd think a multi-billion parameter AI could solve a puzzle a kid could figure out in a minute. Well, you'd be wrong. And here is what GPT-4 came up with. At a quick glance, it kind of looks like a plan. It's using all the right words, the structure seems okay, but it is completely and fundamentally broken. The plan tries to do things that are physically impossible, like moving a block that's still buried under another one. This isn't just a bad plan, it's an invalid one. And this just perfectly highlights the core problem. Now, this failure isn't just a bug, it's actually a core feature of how these models work, and it's been a major roadblock for building truly autonomous AI agents. They are masters of language, not logic. The best way to think about them is as eloquent idiots. They can sound incredibly smart, but they lack a real functional grasp of cause and effect. The paper frames this perfectly with two ideas. On one side, you've got linguistic competence. That's knowing how to say something so it sounds plausible. And LLMs, they're amazing at this. They can generate text that looks exactly like a correct plan. But then there's functional competence, knowing what to say that's actually true, logical, and possible. See, they're just predicting the next most likely word, not the next valid move in a puzzle. And that is a massive difference.
So this leads to a really crucial insight. The answer isn't just to keep building bigger and bigger models hoping they'll magically learn logic. That's a dead end. The much smarter, more elegant solution is to recognize what the LLM is good at, which is language, and what it's bad at, planning, and then just give it the right tool for the job it can't do.
And that brings us to the brilliant idea at the heart of this research, something they call LLM+P, which stands for LM plus Planner. I love this analogy for it. Imagine you've hired a world-class poet, but now you need to get your taxes done. You don't try to teach the poet advanced tax law, you just hand them a calculator.
And that's the whole philosophy right there. Let the LLM be the poet, the eloquent, easy-to-talk-to interface. But for the serious, hardcore logical planning, you give it a specialized deterministic tool, the calculator. This hybrid approach really gives you the best of both worlds. You get the intuitive human interaction and the provably correct reasoning.
So what is this calculator for planning? Well, it's a language called PDDL. It's been a cornerstone of classical AI for decades. Think of it as a super strict, no-nonsense programming language for describing problems. You define your objects, the rules of the game, your start, and your goal. There's no ambiguity. A classical planner that reads PDDL doesn't guess. It just finds a logically perfect solution, guaranteed.
The whole system is just this beautiful three-step process. First, you tell the LLM the problem in plain English. Its only job is to translate that into a formal PDDL file. Second, you hand that file off to the classical planner. It does all the real thinking and spits out a 100% correct plan. And finally, you give that plan back to the LLM to translate it into a simple, human-friendly explanation. The real key here is that the LLM basically becomes a universal translator. It's the perfect bridge between our messy, everyday human language and the crisp, logical world of the planner. The LLM never actually solves the problem itself. It just reformats the question for the expert tool and then formats the answer back for us. It's not the worker, it's the manager.
Okay, but wait, how do you teach an LLM to speak a whole new language like PDDL? Do you need to do all this expensive retraining? No, and this is the most brilliant part. You just give it one single example. In the prompt, you show it an English problem and the correct PDDL translation for it. That's it. It's called in-context learning. Just by seeing that pattern once, the model figures out the rules and can then translate totally new problems. It's incredible. So this all sounds fantastic in theory, right? It's elegant, it's simple, but does the darn thing actually work better than just asking the LLM to solve the problem directly? The results are, well, they're pretty staggering. Oh yeah, it works. The numbers here really do speak for themselves. Look at this. When they used the LLM as the planner, the success rate on that blocks world puzzle was a measly 30%. But with the LLM+P approach,
a 90% success rate. And for another task, it went from 50% success all the way to a perfect 100%. This isn't a small improvement. It's a total game changer. It's the difference between failing most of the time and succeeding almost every single time.
Okay. Solving puzzles on a computer is one thing. But can this approach actually guide a physical robot through a messy, real-world task? To find out, the researchers gave a robot a classic chore: tidy up the room.
So here's the mission. The robot is at a coffee table, and it needs to move that mustard bottle all the way to the pantry. But on the way, it also has to grab an empty soup can from another table and toss it in the recycling. It's your standard multi-step, clean the house kind of task. Now, what's the smartest way to do this? The LLM-only approach came up with a pretty dumb plan. Take the bottle all the way to the pantry, then come all the way back for the soup can. Super inefficient. But the LLM+P plan, now that was clever. It had the robot pick up the bottle, go to the side table, put the bottle down for a second, deal with the soup can, and then pick the bottle back up and continue to the pantry. That's a seriously intelligent plan that saves a ton of time and energy.
And we can actually put a number on that cleverness. The optimal plan from LLM+P had a total travel cost of 22. The naive, inefficient plan from the LLM alone, a cost of 31. That's almost a 30% improvement in efficiency, all because it handed off the hard thinking to a tool that was built for it.
So what's the big picture here? What does all this mean for the future of building AI? Well, this research really points to a powerful new way of thinking. It's not about building one giant monolithic model that can do everything. It's about building agents that work smarter, not harder, by combining simple parts into a powerful system.
For anybody out there actually building AI agents today, the takeaways are crystal clear. Use your LLM for what it's best at, being the most amazing, user-friendly, natural language interface ever created. But for anything that needs hardcore logic or math or following strict rules, delegate that work to a specialized tool. You can build unbelievably robust and complex systems this way, just by teaching the LLM how to use new tools as it needs them.
This paper provides such a powerful framework, but it also opens up some really fascinating questions about what's next. So let's have a little fun. Where could this research possibly go from here?
Right now, the LLM+P setup depends on a human expert to write that PDDL file, that rulebook for the world. But what if it didn't? What if the agent could learn those rules all by itself? What if it could become its own toolmaker?
Imagine an agent. Let's call it the agentic toolsmith. This AI wouldn't just use tools, it would forge them. It could read the API documentation for a new piece of software and just autonomously write the PDO file that describes how to use it. It could watch a YouTube video of someone assembling a chair and figure out the rules of the task on its own. This would let an agent enter a totally new situation, teach itself the rules, and then plan perfectly. That's the real next step, going from a tool user to a toolsmith.
This is for entertainment purposes only.